Hello and welcome to PyData Global 2021. My name is Tanya. I'm your moderator for the session. And please, if you feel comfortable in doing so, rename yourself to the name you would like to be called in the session. And if you want to also add your pronouns so we can address you properly if you ask any questions. Please note, we are recording the session so you can have a look at it afterwards if you've missed something or just want to have another look at it. So our workshop today has the title Data Processing at Scale, and I will just quickly introduce the group of speakers to you, and then we can get started. So we have Benjamin Seidlin, who's System Software Manager at NVIDIA and a long-time contributor to the Python and PyData ecosystem. We have James Bourbeau, who's lead open source engineer at Coiled and will have a talk tomorrow about Snowflake and Dask. Martin Durand, who's a former astrophysicist, data scientist, and medical imaging researcher, and now open source contributor and community advocate, who has a talk later today titled All You Need Is ZAR at 7 p.m. UTC. We have Matthew Powers, tech evangelist at Coiled, also author of 2 books and a popular blog. And he had a talk yesterday about why Pocket files are better than CSV, so you can check the recording of this. And last but not least, we have Richard Zamora, senior systems software engineer at NVIDIA and also frequent contributor to the Dask data frame. So guys, the stage is yours. Have fun.
Thanks, Tanya. Again, my name is Ben. I'm going to share my screen throughout this presentation. So if people want to move back and forth, let me know. Yeah, so as Tanya said, we're going to be talking about data processing at scale. All of us are contributors to PyData, to the Dask ecosystem, and we work at 3 different companies at NVIDIA, Coiled, and Anaconda. And it's really great that all of us can continue collaborating around a really crucial piece of software. All right, so you have this nice kind of single line sentence here. High performance isn't about doing one thing well, it's about doing nothing poorly. So as anybody kind of goes down the path of either high performance computing or scaling their application, they'll find that as they solve one problem, they'll hit another. They first go down the path of, I need my compute to be as fast as possible, and they start maybe making chips faster. And then as you start connecting many machines together, you'll find that network communication actually becomes a problem. And as you explore faster network communication, you'll find, oh, actually my application is dependent on loading data from disk as fast as possible onto the CPU or GPU or TPU. So we really have to think about how to make all of these things kind of work in harmony together, and not any one of them kind of overrides another one. So we're mostly going to be in this talk. We're mostly going to be focusing on cloud parts around kind of pulling data from data stores like S3 or more newer technologies like Delta Lake or Iceberg, and thinking about how to get Dask to work with these larger systems, or how Dask can leverage other binary formats, Parquet, and do as little work as possible to give the best throughput for a given workflow. So here's kind of a brief overview of the talk, where we've segmented it around our faces, though not our names. So maybe we can kick it over to Matt Powers just to start us off on what the kind of problems that we hit at scale, which look very different than running on a single machine, and motivate why we've been improving, or the kinds of improvements that we've pushed into Dask and the larger PyData ecosystem. Matt, maybe you want to introduce yourself and move on.
Sure thing. Sounds great. So my name is Matthew Powers. I used to work in Spark for around 7 years. Recently switched over to the Dask side of things. I've been loving Dask. I think that I'm a huge fanboy of both Spark and Dask, but loving Dask so far, and really excited to show you some cool developments and recent improvements in Dask. So next slide, please. So what's really cool about Dask right now is it's become a great option for ETL. So Dask plays very nicely with a variety of systems. It has great Parquet support, and it can interact with lots of different types of databases. So I'm going to talk about Dask at a high level, kind of cluster computing at a high level, and then I'll be passing it off to some of the other folks for more detailed dives. Rick is going to give a good overview of Dask and then talk about the Parquet stuff in particular. James is going to talk about when we do huge scaling, what type of additional challenges we run into, like as we go from 1 terabyte to 100 terabytes. And then Martin is going to chat about other ecosystem improvements. So it's going to be a great talk. A lot of these guys are my kind of code idols. I see them on pull requests and stuff like that. I just kind of am in awe of their code. So kind of nervous giving them the introduction and honored. Next slide, please. So this slide is to kind of motivate why we care about ETL and kind of this kind of more the boring stuff and not the cool ML stuff. And this is an image from a Google study. And each box represents how much time was spent on different tasks in building a production grade ML system. And we can see that in that little box in the middle, that was the actual ML code part. And then these other boxes like data collection, verification, monitoring, servers, that was the majority of the time was spent on that. And in the real world, when you're building these systems, the ETL stuff is really important in solving the cool ML problems that you want to get to. So that's part of the reason why we've devoted a lot of resources to making ETL awesome with Dask. Next slide, please. So this is just kind of a high level diagram showing the type of ETL we can do with Dask. So it's no problem to read a bunch of CSV files, do some filtering, transformations, aggregations, write out some Parquet files, and then perhaps visualize those on a dashboard. So Dask is a great option for these type of ETL workflows. Next slide, please. So another thing that's great about Dask is it has great interop with other types of systems. So let's suppose you have a Spark ETL pipeline and you're reading in CSV files and doing a bunch of transformations and writing out Parquet. Now, those Parquet files can easily be read into a Dask cluster to train a machine learning model. So you can kind of pick and choose and compose your ETL pipelines and put Dask in there when it makes the most sense. We see a lot of people love doing this when they're like, oh yeah, we want to use Dask, that model that Dask provides easy access to. So they just kind of jump in there and read in some Parquet files that were outputted by another system. Next slide, please. So another thing that's great about Dask is it can read in data from a variety of different types of databases. So we have connectors for Snowflake. The BigQuery one is in development, and the MongoDB one exists. I think James is going to talk about the Snowflake one tomorrow. That's a really cool connector because it has parallel I/O, so it's super fast. Next slide, please. Okay, so shifting modes a little bit. In this talk, we're going to be chatting a lot about the Parquet file format. The Parquet file format has become probably the most important file format in the big data space for a variety of reasons. So we're going to talk about it at a very low level, as we should, because we're going to be getting talks directly from these core developers who are doing this low-level work. And before we dive into the low-level stuff, I just wanted to cover some high-level benefits of Parquet, just so there's some higher-level context. So at a high level, Parquet gives us some really nice benefits, like there's the schema in the file footer, so we don't need to infer it. It's a columnar file format, which means it's more compressible and results in smaller file sizes. Columnar file formats also allow for column pruning, which in cluster environments can be a huge performance gain. Parquet files organize data in row groups, which has metadata and allows for predicate pushdown filtering. And all of these Parquet features are fully supported in Dask, so you can take full advantage of them. Next slide, please. So this little diagram here is showing, comparing kind of CSVs and Parquet files with the schema. So, right, if you have a CSV file, you either need to infer the schema or manually specify it. Both of those are potentially computationally expensive. They're annoying, they're error prone. Who wants to do that? With Parquet files, we can just grab the schema from the file footer or potentially from a metadata file. We'll be talking a lot about grabbing schemas from Parquet files. So it's good to have this intuition that in Parquet files, the schema exists in the file footer metadata. Next slide, please. This slide's trying to give you some intuition on the difference between row-based file formats and columnar file formats. So row-based file formats stores data in rows. Columnar file formats are kind of like a transposed version of a row-based file format. And one cool thing about columnar file formats is that they store similar types closer to each other. Compression algorithms really like that. And that's why columnar files like Parquet are more compressible than row-based file formats like CSV. Next slide, please. Another amazing benefit offered by columnar file formats is column pruning. So column pruning means that you can cherry pick certain columns from the file and just send those to the cluster. Now, by cherry picking certain columns, you send less data to the cluster, which is actually a massive performance gain. So in this little example here, we have our cluster of 3 computers. We have our data file that has 6 columns. Now, suppose we're running a query that only needs 3 of those columns of data. We can just send those 3 columns over to the cluster. Now, if you're using a row-based file format like CSV, that's not possible, but with Parquet, that's possible. Next slide, please. Another great performance benefit we get from Parquet files is row group filtering. Now, similar to the column pruning, whenever you can send less data to the cluster, you can expect a big performance gain in your query. Now, Parquet files have row group metadata on columns, and certain filtering queries can be structured so that you're only sending certain row groups to the cluster rather than all of them, which can be a huge performance gain. I actually, in my talk yesterday, I showed a query that when you use predicate pushdown filtering with Parquet, you get a 25x performance gain. So feel free to watch that talk if you want to see some more examples. Next slide, please. Okay, so now I'm going to pass it over to Rick. He is going to talk about Dask at a high level, and then he's going to dive into those Parquet concepts that I just covered in much more detail. And Rick is a Parquet genius, so you're in for a real treat.
Thanks for the introduction, Matt. Yeah, so my name is Rick Zamora. I'm a engineer at NVIDIA and a pretty frequent contributor to Dask data frame. And so, yeah, since in this workshop, we're really focusing on the use of Dask and the Parquet format for doing big data processing, it makes a lot of sense for us to first start with, an overview of what Dask is and what Parquet is and how they're integrated. So let's get started with that. Next slide, please. So yeah, we'll start with the Dask introduction. And so what is Dask? It's a flexible library for parallel computing in Python with sort of emphasis on flexible in Python here. In order to understand what Dask is, there's a pretty broad Dask ecosystem with lots of different projects that tie into Dask. But for the purposes of this talk, we can understand Dask as really being a combination of 3 general components: a core library, a distributed library, and then these collection APIs that users typically use to interact with or use Dask. So next slide. So the first component of Dask that we'll talk about, we'll refer to as the core library. And you can think of the core library as being where the implementations are for single machine task scheduling engines. I think from here on out, I'll probably just refer to these as the schedulers. But so a single machine scheduler would be something that's going to be able to schedule your work within a single machine, whether you're in parallel using multiple threads or multiple processes on that single machine. And so the three schedulers that are included there are the threaded scheduler, the multi-process scheduler, and a synchronous scheduler, which is really just threaded scheduler, but with one thread. So it says, let's do everything on one thread. The core library also includes generally a task graph specification, which is actually pretty simple. It's just a Python dictionary of tuples. I'm not going to go into the nitty-gritty details of exactly all the details of a task graph and how we also use things like high-level graphs. But what you should understand is that in this task graph, the nodes of the graph are just going to be some form of computation, some computation function. And then the edges between those nodes in the graph would just be dependencies of the outputs of those tasks. All right, next slide. Okay, so in addition to the core engine of DAS, there's also the distributed engine. I mentioned before that in the core engine, we have the single machine schedulers. That doesn't help a lot when you want, to work on on a cluster with many distributed machines. And so in order to use distributed scheduling, you actually need a separate Python package called distributed. So it's really just an addition. So if you want to, the distributed package is going to depend on the core Dask engine for most of the logic, but then this allows you to actually schedule and execute the tasks in a distributed manner. Next slide, please. And so the last component that I think is really important are the Dask collection APIs, or the big data collection APIs are often referred to as. And so the purpose of these collection APIs is that this is really where most users are going to interact with Dask. Most users are not going to need to know how to construct a custom task graph and execute it on all the workers. They're going to be using something like Dask Array or Dask Data Frame so that they can work with an API that looks similar to something else in the PyData ecosystem. So if you're working with array data, you'll want to use Dask Array because the API is going to look a lot like NumPy. And if you're using tabular data, you're going to work with something like Dask Data Frame because the API is going to look just like pandas. Like I mentioned before, the general purpose here is just to make graph construction and execution pretty much invisible to the user. Next slide. And so since the collection APIs really are important, this is just like another perspective, another way of understanding. I already mentioned that NumPy is sort of what we are basing Dask Array on. So on the left, you see if you would normally be dealing with a really large array, maybe something that doesn't fit in memory or something that's large enough that you can get a performance boost by doing the computations in parallel. Instead of working with one large NumPy array, you can work with a collection of smaller NumPy arrays that would be arranged, on some grid, some ND grid. And then for pandas, the same thing is true. So instead of working with one extremely large data frame that maybe won't fit in a single machine's memory, or maybe it's large enough that you can get a performance boost by executing it in parallel, you would just use Dask Data Frame API, and the API would look very similar to what you would get with pandas. So like dd.readcsv looks just like pd.readcsv. The group by and commands look pretty much the same. They look exactly the same. All right, next slide. Okay, so at this point, we really understand the basics of what Dask is. So moving from the left, we start with some collection API that the user is typically going to interact with, something that looks familiar, looks like other PyData APIs like NumPy and Pandas. What's happening under the hood is that you are constructing a task graph. That task graph can then just be executed using some single machine scheduler or a distributed scheduler. All right, next slide. Okay, now that we have that big picture in mind, I'm going to kind of step back and go through some details of things like Dask Data Frame and the Dask Distributed, because these are really important for this general workshop. So for Dask Data Frame, I already mentioned that when you are working with really large tabular data, Dask Data Frame allows you to break that data set into many different pieces. And what we actually call each of these pieces in Dask Data Frame is a partition. So you may hear me or other speakers refer to partitions. Under the, inside of Dask, when you're working with a data frame in Dask, you're actually working with a Dask Data Frame collection. So that class or that object that you're working with actually is a collection of many small pandas data frames. And then in order to understand how different operations are going to modify this data without actually having to process the data. We also carry around something called metadata. You can just think of metadata as usually being an empty data frame object, something that kind of provides a schema, so we know what the column names are, we know what the data types are, and if we do some sort of operation like adding a column or doing some kind of multiplication or group by, we know how that operation is going to modify the data without actually having to read it in. Next slide. And so I already mentioned, well, what is the purpose of using a data frame, of using a collection API like Dask data frame? It's really so that we are hiding graph construction from the user, but allowing them to use, the Dask engine of parallel execution, graph execution. And so this is what's happening for a simple example, like read CSV. If you have a data set that's large enough that if you call read CSV, the read CSV logic will pretty much take some default chunk size and say, oh, this data is big enough that I'm going to break it into 2 pieces. And so once it has that basic information in mind, it's going to build a graph and say, okay, well, I'm going to read partition 0 up here on the top. And then separately, I'm going to read partition 1 in a separate task down at the bottom. And then if I'm doing a group by aggregation, I might need to do a group by aggregation on each of these partitions. And then I'm going to do some sort of tree reduction and build a graph that way. And so this is all invisible to the user, but this is exactly what's going on under the hood. Next slide. And so now that we understand what these collection APIs are actually doing, they're building a task graph so that it can be executed with one of Dask's scheduling engines. It's also important to understand that this is all lazy, the graph construction at least. So what happens when you use something like read CSV and then you calculate unique categories and everything like that, that's relatively free. So, I mean, you're doing a little bit of file system work to figure out where the files are and how big they are for read CSV, but that's still, practically free. And then calculating the categories, you're just building a task graph. You can see I show the wall time is just, a millisecond here. So you're not really doing any work. You're not really processing any data yet. What you need to do with these collection APIs is call something like compute or persist to actually execute the graph. And so I'm just going to really quickly here go over the difference between compute and persist, because it can be pretty important for new users to understand, hey, why am I blowing up the memory on my client process? Everything's going crazy. Well, if you call compute, what you're actually doing is you're materializing an in-memory pandas object on your client process. So if the output of your, like if you want to read in a full data set and you let's say you just call read CSV and then you compute that DDF, what you're actually doing is moving all of that data into one pandas data frame on your client process. And so that can be a problem. So it's not recommended if your output of your compute is something big, it's not just like one number or just like a file name, then you probably don't want to call compute. Instead, you probably want to call something like persist. What persist does is it executes your graph, but it preserves your collection. So you keep all your data in distributed memory if you're using Dask distributed. So that leads us to the next slide. Yeah, so like we just went back and talked a little bit more about Dask data frame. Dask distributed is also very important for scaling to large systems. When you're using Dask distributed, you have to kind of have an understanding of you're breaking the usage of Dask into 3 parts. First, you have the client process. The client is where you're actually using the Dask data frame API. This is where you're going to be running your Jupyter notebook probably here, or running your Python script that's using Dask. And what you're doing is you're constructing the graph on this client process. And then separate from the client process, you have a Dask cluster that you need to deploy. I'll go into details about that after this. But what the cluster is going to include is a scheduler process and then some arbitrary number of worker processes. So what happens when you're using Dask with Dask distributed is your client, you're going to construct a graph, you're going to send it to the scheduler. The scheduler is then going to process that graph and schedule the work on all of these workers. And so this is just so you have the idea of when we talk about the cluster, the scheduler, the workers, the client, this is what I mean. All right, next slide. Yeah, so I just mentioned there are many ways to actually deploy a cluster. If you are using Dask, just distributed library, you could do this manually with something like the Dask scheduler or Dask worker command line interface. There are also many convenient cluster managers out there. Like if you're working with Kubernetes, there's Dask Kubernetes. If you're working with like on an HPC system where you have SSH, you can use an SSH cluster or a spec cluster. Also here at the bottom, I show a really convenient API available with Dask with distributed called local cluster. So this is if you kind of want like a quick start for getting, for using Dask distributed, and you just want to work on a single machine that has multiple cores, you can use the local cluster to get started. All right, next slide. Yeah, and so the last thing I'm going to say about like Dask at a high level is that, and also Dask distributed, is that it offers this nice interactive dashboard with Dask distributed. So when you spin up a cluster, you'll typically create a dashboard process as well, which will be sampling metrics at runtime. And so this is a really beautiful way to build intuition about the performance that you're getting. So sometimes people will run into issues because they might have defined some kind of compute task that is running into problems or taking forever. And if you're using your interactive dashboard, it's really easy to see, oh, it's this task right here that's just taking forever. And so it helps you build intuition. All right, next slide. Okay, so that was our brief introduction to Dask. There's obviously a lot of things that we could talk about. I can give probably a 2-hour talk on Dask itself, but for the sake of time, we're going to move over to Parquet and how it is implemented, how it can be used with Dask. Next slide. So Parquet, what is it? Matt already went into details about Parquet, so I'm really going to be reiterating a lot of what he said, and then kind of talking about the API used within Dask data frame. So what is Parquet? It's a binary columnar storage format. It's designed with things like parallelism, compression, and generally performance in mind. When you imagine a Parquet data set, you should just be imagining a collection of Parquet formatted files. These files are, sometimes they're partitioned by directories using like Hive partitioning, but for the sake of simplicity, we can just imagine them as a collection of files. And within each of these files, you're going to have a collection of row groups. Within each of these row groups, you're going to have a collection of column chunks. Each of these column chunks is where the data for a specific column will be stored contiguously. And then within each of these column chunks, it's going to be broken into pages. And the way to understand parallelism, especially if we start with Dask, if you have different Dask tasks, they're usually going to be reading a specific group of files or a specific group of row groups within each task. Same goes for MapReduce. The IO engine itself will usually be parallelizing over multiple column chunks at a time, or maybe multiple pages. And then the encoding and the compression used for Parquet is usually at the page granularity. One other thing to understand about the general Parquet format is that every file has this footer metadata down at the bottom. This footer metadata is great because it tells you exactly where the offsets for all of the column chunks are in your file. It also tells you a lot, optionally, but usually it'll give you statistics about each of those column chunks, which is really important for things like predicate pushdown, so that you can know like the min and max value for each column. It makes it much easier to filter. Okay, next slide. And so a side note on this footer metadata, although it's not in the specification to have what's called a global metadata file, usually named, or in Dask, we assume it's named underscore metadata. So it's not in the Parquet specification to have this file, but in Dask, we do by default write it out, and we do look for it on the read side. And all this is you can imagine if you take your full data set and you take all the footer metadata from every single file and you just aggregate it into one large global metadata object and write that as its own standalone file. And this is really convenient, when you have cloud file systems where it can be pretty expensive to go and fetch the footer metadata for every file in the data set to kind of do the planning stage of where are all the row groups, which columns are we reading? And if we just need to read in one file, it can be much faster. There are, of course, scaling problems with this that we'll get into later, but this is just so you understand what this global metadata file is. Next slide. Okay, so as far as Dask and Parquet, so as far as how Parquet is available in Dask, it's really the same way that it's available in Pandas for anybody who's available with, for anybody who's familiar with Pandas. And so The API for reading in a Parquet data set is just simply read_Parquet. So if you want to read a Parquet data set using Dask, you would just import Dask data frame and call it dd.readParquet and point it to some data source. And it's just the opposite for writing it out of Parquet data set. So if you have a Dask data frame collection like DDF and you want to write it to a Parquet data set, you just call it to_Parquet and you point it to an output directory where you want to write your data set out as what it's going to do by default. It's going to write a distinct file for every one of your partitions in your Dask data frame collection. But there are other options, which I'll mention, I think, in 2 slides. All right, so next slide. All right, so Dask Parquet API, I already mentioned it looks very similar to the Pandas API for reading and writing Parquet data sets. The only way that, and something else that's actually similar is that it's backed by different engines, just like the Parquet, the Pandas Parquet API allows you to either use the PyArrow engine or a fast Parquet engine. We allow the same thing in Dask data frame. And so the implementation is what we would call pluggable, meaning when you use read Parquet or to Parquet, you can specify a string to either PyArrow or fast Parquet, but you could also implement your own engine that inherits from one of these engines or from the base engine, and you could pass that in as well. So this is if you wanted to override, what the logic is for reading out a Parquet partition or the logic for writing one out. You could do that if you wanted to. One thing I'll mention here at the bottom is I'm including Rapids. This is a case where we actually are using this feature of the pluggable nature of the implementation. In Rapids, in Dask QDF, what we're doing is inheriting from the dataset engine and then changing the IO backend to be using QDF instead of something like PyArrow. And one more note I'll make is that we still have this PyArrow legacy option, but it will be deprecated in the near future. So just a warning there. All right, next slide. Okay, so the Dask Parquet to Parquet, I'm not going to go through a whole bunch of details about what all of these options are and how they can be used. I think I'll mention the ones that are most important for scaling. Down at the bottom, I've highlighted this write metadata file option, and it's important. I mentioned, in a lot of cases, you can improve performance by writing out this global metadata file, because on the read side, you then can just look in one place to figure out where all the partitions are, where your output partitions will come from. However, there is non-negligible overhead of writing this file. The way we can't just append to a single file on all of our processes. Instead, we do need one task to sort of aggregate all of the metadata together, tie a nice little bow and write it to disk. And that can be a problem if you're using commodity hardware where you have, we don't have enough memory to do this. And there is some overhead in doing this. The other option I'll mention as well is there's also things like partition on, which means we can do directory partitioning because that can improve filtering on the read side, but it also may result in many small files, which you have to be ready to deal with. And then the final thing is the storage options. This is if you're interacting with cloud storage, you might need to pass things to deal with GCS or with S3. And so this is where you would be adding those options. All right, next slide. And on the read Parquet side, I'm also not going to go into all of these details, but I will, just mention, as Matt mentioned before, you can, cherry pick which columns you actually want to read. So since we are using since the Parquet format separates the column chunks, we can specify which columns we want to read, and we can improve IO performance, considerably. And the same goes for filters. Since we have statistics about each of these column chunks, we can skip over the ones that do not meet certain filters. Like if you only want some, timestamps that are beyond some date, you would definitely want to specify that here because you can end up, skipping over most of the data. And then the other thing is this split row groups. There are ways to control the data frame partitioning. So you might want to have one partition for every row group, or you might want to have one partition for, a whole group of row groups. And this is how you would do it. All right, next slide. Okay, yeah. So that gives us our high level overview of Parquet and Dask. I didn't want to go into too much detail, but I'm happy to follow up, if there are questions, and I'm happy to answer any questions about how Parquet is implemented in Dask and what people should use. But from here, we'll move on to problems at scale with James.
Awesome, thanks, Rick. Hi everyone, I'm James. I'm like many other people on the call, a Dask maintainer, and I work at Coil as well. So yeah, I want to sort of start to talk about some of the issues that we run in whenever you take these, sort of Parquet workloads and scale them up to very large data sets on very large clusters. I do want to just kind of note at the top that how Dask exists today, it works very well for ETL workloads and really a lot of commonly used scales. So for instance, if we go to the next slide, actually, here's a sort of a motivating example. This example, what we do, there's sort of 3 steps that are kind of representative of many workloads. I have an actual example workload on the right-hand side with some real code. So the first step is we read in our data set. So like Rick just talked about, we can use Dask's read Parquet functionality to read in some large data set on S3 using, for instance, the PyArrow Parquet engine. We can also use fast Parquet. So that's sort of the initial data access step. We then followed up by doing some kind of processing on the data frame. In this example, I'm constructing a new column, this is kind of a contrived example, but a new column which is some function of of other columns in the data set to create some new derived column for the data set. I then, after processing this data set, take the data set and use Dask's toParquet functionality to write out this new processed version of the data set to some S3 bucket. So this is typically what we see. We see some kind of IO process IO to write back out results to somewhere. We see this type of workload in many different applications. You can imagine swapping out the process data step that's here right now, the supply, to be, apply some machine learning model to your data set to make some predictions that you then save, those predictions to another Parquet data set. These types of workloads work very well with Dask as it is, at the gigabyte scale, tens of gigabytes, hundreds of gigabytes, terabyte scale. Once you start pushing things to thousands and thousands of workers and maybe tens and hundreds of terabytes, then you'll notice there are some things that start to break down, which I'll highlight in the next few slides. This is really just a way to tee up Martin in the next section to talk about some of the improvements, recent improvements in Dask, where we have gone through sort of resolving some of these issues. And Ben, in the last section, will talk about some of the more systemic issues. We'll talk about some longer term visions for solving those issues as well. Next slide. Yeah, so one issue that folks run into, specifically when using Parquet and Dask, whenever data frames have many partitions. So we have tons of pandas data frames that comprise our Dask data frame. This consolidated metadata file that Rick was talking about that stores sort of the metadata for all the individual partitions can become very large. This actually becomes, and when I say very large, I mean can be order gigabytes, which can be unfortunate when you're reading and writing using Parquet. I'm linking there to a couple of GitHub issues so you can see real world examples where this type of issue has cropped up. I should say that today it's possible to not write that consolidated metadata file out. That's one sort of not solution, but workaround is, hey, I'm actually not going to write out this consolidated metadata file for my super large data sets. The issue is that can make subsequent reads slow. So, whenever there's a reason this metadata file exists to begin with. Otherwise, we'd have to go through and sort of serially process, read in every partition in our data set. Load in its data and sort of construct the equivalent of this metadata file on the fly. And that itself can be very slow when you have these large data sets with many partitions. And it's interesting, you'll run into lots of, rather like we ran into issues with this large metadata file in lots of different spots in the software stack. For instance, there was a PyArrow issue. We were talking about using the PyArrow Parquet engine inside Dask there was some issue with the actual loading in Parquet of these large metadata files. There was some issue with thrift. This has since been resolved. So sort of giving you a sneak peek for the improvement section. But yeah, issues like this have cropped up, and we're sort of going through and taking care of them as we go. Next slide, please. When scaling up your workloads, there's lots of, this doesn't always mean scaling to the cloud, but today it actually largely does mean moving to the cloud. Although you may have access to a giant machine that you can just have a local cluster on and not have to go to cloud, or maybe you have access to some HPC system. Maybe you have a Slurm job queuing system or something along those lines, in which case you don't have to move to the cloud to scale to these large workloads. But for many people, it does mean scaling to the cloud. There's actually several sort of considerations when scaling to the cloud that you have to keep in mind. One is the environment of the workers. This means that, Dask, what it'll actually do, so whenever Rick was talking about sort of constructing the graph, that will happen wherever you are running Dask code. So that may be in your Python script or in your Jupyter notebook. You're actually going to construct the graph there, and Dask will take all of the things you want it to do. So like, it'll take the read Parquet calls, it'll take the NumPy sum call, and actually ship those off to the workers. That means that your workers have to have a consistent environment with wherever you may be running your Python code. So you need to make sure you have, for instance, PyArrow installed on the workers in the same version of PyArrow that you have installed locally on, say, your laptop where you have your Dask client session. So that's sort of one consideration that comes whenever you're scaling from a single machine to multiple machines. You also have to worry about securing the cluster. And I guess really what I mean by that is a couple of points. Securing the cluster in the sense of like provisioning nodes. So you have to understand how to spin up, say, EC2 instance on AWS, if that's sort of the cloud provider you're using, or the equivalent in GCP or Azure. You have to worry about actually spinning up those nodes, as well as making sure they're all connected in the same network and have access to one another. Another thing is you have to make sure that things are properly secured in a security sense. I'm using the same word several times, but you have to make sure that, for instance, you might want to use encryption whenever you're communicating messages from one node to another. So making sure you have the appropriate TLS certificates set up for Dask to support that. Whenever you move from one machine to another machine, you also have to worry about sort of the permissions model and credentials for various data access. So you may have your, for instance, local laptop configured to, you have your AWS config file set up where you can access S3 buckets locally from your machine. But you need to make sure that the workers you're using have the same access to access, S3 or Google or Azure blob storage or whatever data store you may be using. Luckily, FSSpec, which I linked to the documentation there and has been talked about already in the talk, which Martin maintains actually, along with others, it bridges the gap between a lot of these different storage backends. So FSSpec is sort of, Martin can elaborate more on it, but my definition of it would be a sort of uniform API for file storage access. So it doesn't matter whether or not you're using a local file system or accessing files on GitHub or accessing files in S3 or Google or Azure or files in Dropbox. They all have a sort of uniform interface for doing operations like opening files, reading files, writing files, listing files, things along those lines. And so FSSpec has done a really great job of sort of unifying data access. That said, there are still differences between the various storage backends, which sort of the differences between these become important at scale. Next slide. So once you've sort of taken all these things into consideration, you have your cluster provisioned. It's using encryption between all the different various nodes. You've set up credentials so that you can access all of your data at GCP on all of your workers. There's still other things that other issues you'll run into when doing these large ETL loads. One is file system caching. So there is this desire in cloud storage to cache results. That's to avoid sort of repeating expensive operations. This is great from a performance perspective, but from a consistency perspective can be less than ideal. I'm linking there to an issue where there was some interesting errors arising because of these inconsistencies due to file system caching. Another type or class of issue that you'll run into is limits. So linking it to another issue where you'll start to hit things like S3 limits. In particular, if you have some huge 10,000 worker cluster doing S3 things, hitting S3 endpoints, you'll see that you'll have that. What that means is you have like 10,000 workers concurrently hitting S3 and maybe hitting it multiple threads at the same time. So you can pretty easily hit in S3 or cloud throttling limits. There are ways around this with retries, but this is something that folks do run into. Another is partial writes, which Ben will talk about later, due to sort of ephemeral workers. Maybe you're using spot instances in your cluster, or maybe you're auto scaling. And so you have workers coming and going throughout your computation. Anyways, these are sort of the types of problems that folks run into. I've linked to a few relevant issues for real world examples. And now, next slide, I'll turn it over to Martin to talk about some of the recent ecosystem improvements to help resolve some of these issues. Take it away, Martin.
Hi, thank you. My brief introduction, I work at Anaconda. I've had this job for 6 years, working mainly on open source. I'm the principal author of FastParquet and FSpec, as you just heard. So what has happened in the Dask ecosystem to try and make some of the problems you just heard about go away, or at least not be quite so important? So next slide, please. I should say these first couple of things, the developments within Dask itself was mainly done by Rick, but there were a few more people, including myself, who are involved with this. But yeah, Rick gets the majority of the credit here. One thing that you just heard about is what if your Parquet dataset consists of very, very many pieces. Those pieces usually we think of many row groups and many files. This creates a very large Dask graph, and that puts strain principally on your scheduler. So one thing you might want to do is to have each of your tasks read several parts of your overall data set. And this we call the aggregation. And there are a couple of things that you can do to grab these into tasks. And having done that, first you need to analyze your data set to know what the pieces are. But once you form your task graph, the end result can be that your task graph is much smaller than it would have been otherwise. And that means that the scheduler doesn't work as hard. It doesn't need to take up as much memory for the graph itself. At the cost of, obviously, each of your partitions is going to take up more memory. So it's a trade-off, and many of these things are trade-offs because when you reach the real big size limits, then you have to think a little bit more carefully about the processing that you're having to do. There's some code example here that we won't go over now, but we can talk about it later. Next slide, please. We talked about this metadata file a bit. So this is something that is since quite I think 2 or 3 years, maybe more in Spark, this is no longer the default to write this. And so we already were facing the case that the metadata file might not be present. So we were able to cope with that. But even if it is present, you might choose not to read it. And the reason is, even though it would be a single read to get all of your metadata across the whole of your data set, it nevertheless can be quite big, and this processing of the metadata file itself was done in the client. So it's a serial process that might use lots of memory. If it isn't there, then in order to process all of your data, you need to be able to find out the metadata of at least each piece in the workers. So you end up using more CPU overall, but you can spread that CPU use over your workers. So ignoring the metadata file is now an option, and you may choose to use it. And it might bring you great improvements in the case that your metadata file is very big. However, it doesn't always help you. So it's another trade-off that you need to think about. Moving on. So as a kind of summary, those are two detail slides that we can come back to if there are questions. But there are some other improvements that have happened specifically within Dask. So the first one is the counterpart to what I just said. You might choose not to read a metadata file in some cases. Well, in that case, maybe for that particular data set, there's actually no point to write the metadata. And that will save you time when you do the writing, because you don't need to have the extra task that does this metadata write. And that task can actually be very heavy too, because it needs to wait on all of the metadata pieces from all of the previous tasks and merge them into a single thing. And that single thing can then take up a lot of memory, and it might fail, which will leave you in a bad position. So now you have the choice not to do that. The aggregation I already mentioned, but it's an interesting option, and actually you can aggregate at various levels. So please read the documentation carefully, because it takes a little bit of getting your head around how that works. And again, on the metadata, now that we have the option not to use a metadata file, you can do the processing of the metadata so that you can set up your task graph also on the workers. That's a relatively new feature. And it's, again, an interesting thing that you are trading off efficiency for speed across the network to get all of your workers to do a little bit of processing for you. So it's a sort of Dasky thing to do, but having Dask do work so that you can set up your data frame in the first place was something that took us a bit of convincing that this was a good idea. Final couple of points here. Spark conformers, we did put some work in making some of the quirks that were a little bit different between how Dask operated and how Spark operated go away, specifically by comparing workloads and specific data sets across Spark and Dask. So that is ongoing. We haven't covered everything, but we've definitely covered at least a couple of cases. And finally, I'll mention this again in a moment, PyArrow itself has changed quite a lot over the last couple of years. Particularly, they've brought in a new API for data I/O called Dataset. And so within the Arrow arm of the code in Dask, you can now access either the old Arrow API or the new one. And they both come with similar set of options, but not everything is identical. So it's worth understanding that there is this difference. The new API is the only one that will be supported eventually. I'm not sure when the old legacy API will be dropped, but at some point it will. Moving on. So those are things that happen specifically within Dask itself, but other things have happened in the ecosystem, which is what I'm mainly supposed to be talking about, but this has been quite covered in other places. So there's a link here to my blog about specifically FastParquet, and I'm happy to go over the details of what all of these things mean, but there's quite a lot of detail, so I will only go into it if people are interested. But suffice to say, there were a lot of changes, and this was a pretty major push of mine over the months leading up to August when it was finally released. And a lot of things happen. We reduced the dependencies of FastParquet so that importing it is faster, and the minimal environment it takes to install it is much smaller. We also brought in a load of new features, including the Parquet v2 data pages, which come with some performance improvements, new types, optional filtering, new encodings, and also a real drive to get performance better, at least on the read side. And there are some benchmarks that are shown again in this blog. And then the final one, this has not been merged or released, but I am very happy that it works, just a little scared to put it out into the wild, is to rewrite thrift in my own custom Python code so that we don't depend on thrift anymore. And it's actually much faster. It's not as conformant, let's say. It's not the industry standard, it's my own code. So that's the reason that I've held off. And it would also require some changes within Dask and other dependent projects to use it. So it would take a bit of effort and coordination to bring that about. Next slide. Similarly, and actually partly driven by the same process that I was trying to optimize FastParquet, it turns out that the IO layer has a lot of optimization possibilities, such as even on a local file system, a surprising amount of time is spent managing strings so that you can get the paths right and checking for each of those strings, does the file exist, how big is the file, and opening the file. And if you have a file, a data set made up of thousands of files, these things add up. So some smarts about how you do this have really resulted in pretty substantial speedups in very specific workloads. So this is what happens when you do benchmark-driven development, as Ben alluded to at the start. You can improve specific things and not necessarily make a difference to the typical workflow. So all of these things need to be done with a mind to, am I actually making things worse for anybody else? And I think on the whole, FSPec has improved in a way that matters to Parquet. So I mentioned that one. Also in S3 and some of the other remote file systems, try to get rid of redundant calls. These are typically in the file info and file listing layer, not the actual access of files. The third one is something that we're still actually actively working on because it's hard to get right. You heard that we need to do retries sometimes because the cloud systems will only take so many requests per second. But at what level to do these retries and exactly what pattern of retries you want to do is complicated. If you allow for lots of retries, then something that genuinely fails for some reason might take a very long time to tell you that it's failed. On the other hand, as you increase the number of requests, a certain fraction of them will fail. So you need more retries. The bigger your workload, the more retries you will need. You also need to retry specific things, like if the request comes back actually saying, for example, one of the messages you may get is, your quota of requests for this second has been exceeded, please try again later. You need to recognize that, and you need to wait an appropriate amount of time before trying again. Other things like server cannot be found are retried on a completely different level. So there are many things that interact here, and it's quite difficult to get around. And this is why this is still a work in progress. Concurrent fetching of data from remote has been in FSPec for a while now for S3, GCSFS, and Azure and HTTP. Actually making use of those is a work in progress on the Parquet side. FSPec supports a bunch of backends, and there are more coming, so that's interesting read. The core ones that we're talking about here have been around for a while, though. And all of these different projects, the FSPec is like the core, but there are many packages now that depend on it, and we are reorganizing ourselves to be able to give users more clear channels for feedback and conversation. So there is an FSPec org on GitHub that already exists, but only contains just the one package for the moment. Well, we aim to do this. One particularly interesting thing, and I include this only partly because I'm going to be talking about it later today in the talk All You Need Is Are, is the idea of Kachunk, which is a package to make virtual file systems out of paths that exist in different places. This is interesting for Parquet because Parquet has a hierarchical directory-oriented dataset model. So you can construct a Parquet dataset of a virtual file system where you don't need to copy the files themselves into a particular directory system in order to make them appear as if they have particular special place within the directory hierarchy. Now, that might have seemed Greek to you, the thing that I just said, but the point of it is that you can use the partitioning logic that Parquet has in order to make a virtual data set, an aggregate data set over many other data sets. We're going to produce some examples of this in action so that you can actually see how it works. So we haven't done that yet, so please look out for that in the future. And then finally, I think this is specifically mentioned in the coming soon, is that you can, since Parquet is special and we know where within a Parquet file all of the byte blocks that we need are, we can prefetch them using FSpec efficiently and be able to get a faster read speed from that. Again, this is coming up, so I refer you to that. Next slide. Now, I don't have many specifics on Arrow itself because I'm not the expert on that, but Arrow has been in constant rapid development over the last, well, actually for quite a long time, but specifically the Parquet part, the dataset API has been improving a lot. And a lot of that improvement has been the ability for Dask in particular to be able to get access to the metadata pieces that it needs to be able to implement the improvements that we've already talked about. So Arrow have been very responsive to our request to be able to surface that metadata. And largely we've been busy in implementing those improvements on the basis of what has been available from Arrow. So we've had quite a lot of back and forth between the two groups to get that right. And yeah, it's largely been try to keep up with the rapid pace of what Arrow is doing. How much of that has resulted in specific improvements in performance, I don't really know, but perhaps we can talk about that afterwards. And I think that's it from me. So handing over to Ben again.
Thanks, Martin. Before I keep going, I wanted to mention why we focused on, in this talk, on S3 and Parquet. So we actually especially in the last few months, but definitely over the last year, we've had a lot of the community, a lot of customers reach out and say, we think that this could be done better in the Dask ecosystem. Many of the workloads from the community and customers were IO limited, that they had data on S3 or GCSFS or some other cloud storage thing. And they also, all their data was in Parquet. So it was obvious for us to focus on those things. However, many of these ideas also translate, as I said, to other cloud storage things, but also to other binary formats like ORC or Avro. And I wanted to also take a moment and reflect on like how we got here, not just as like a PyData community, but like as a data engineering community, like the world at large. Maybe we got here, I don't know for sure, but it seemed like the whole world was on databases probably long before any of us were born. They've been around for a long time, and maybe some of us, the older folks that are around. And databases were great, but we needed to like as individuals or as workflows developed, we needed to do a lot more with the data that was kind of housed in a singular database. More might mean we had scaling problems, more might mean we needed to run like nonlinear functions, or we needed like more customized user-defined functions to be executed on rows. We just needed databases to flex in ways that they hadn't really been designed to. And as the cloud kind of got going, it became such a wonderful place to get globally available data. You didn't spin up eventually people maybe stopped spinning up just a singular MySQL database because S3 offered globally accessible data. That was a huge improvement. And with all these improvements came other pain points. So I'm going to maybe talk briefly about what some of those pain points are, because we needed to, typically these pain points are around custom solutions, that we don't have best practices. As we make these lateral moves of getting like the flexibility that we want in Python and bringing them into databases, or as the lateral moves look like from moving away from databases to these new data storage formats, bringing in security or bringing in high availability, we hit other kinds of problems. So we have these words, we've said database, I'm about to say the word data lake, maybe the word data warehouse. I'm not really clear on these definitions, but maybe a data lake is like, I'm just storing all of my data in S3. And that was, as I was just saying, like that was really great. I get globally accessible data. But we have now a bunch of problems with that. or we have all these custom solutions on top of that because we want to build things that look like, maybe as data comes in, we leverage other tooling in AWS to have some event-driven system. So a new file comes into S3, and now we want to, as soon as new data is there, we want to have SQS or some RabbitMQ or some other queuing system that's monitoring the buckets and saying, oh, as soon as the data comes in, process it in this other way and shove it into a MySQL database for some other kinds of post-processing that I want to do on it. I need to build some other customizations as raw data comes into some global storage system. That, as the first bullet point says, that lake isn't readable while the write is happening. So in my mind, like the canonical example is some windowing operation, some time series thing. I'm pulling in data from an IoT device, or there's some financial transaction or something that's happening on every minute or every hour or every day. It's very easy to quickly achieve the kinds of problems that used to just be reserved for Google or Twitter, or even like the Large Hadron Collider. We can hit these terabyte problems or even petabyte problems much sooner. So we have to scale this solution that we currently have. So we need to be able to do things like listing lots of files. It's very common. We need to be able to handle transactions where the cluster might die. It's really easy to test the limits of AWS and see when a compute node might die or some worker might die. We need to handle deleting a few rows from data. We need to update things. And as we update larger data sets, we want to find other optimizations like combining small files. So for example, if you're writing things every minute or every hour, we might want to compact all that to a day's worth of work. These are the things that used to be canonical inside of databases, that we could run through these operations in a way that didn't destroy the database or destroy like the execution of workloads that were going on concurrently. So to get into a little bit more finer points of we were just saying, we saw lots of examples. Like James showed this example of, we're going to read some data, then we're going to do some analysis, and then we're going to write out. And that's great if it's just you, but that's not going to work if you have 10 users or 10 workflows that need to run simultaneously, where we read in some data and then, we are trying to write some data as we're trying to read from it. This might look more like transactions rather than batch processing. As I said before, when we get to lots and lots of data, if you ever try to list all the files in an S3 bucket where there's 100,000 files or more, you'll feel that. You'll see it happening where you're just twiddling your thumbs for 10 seconds. We want to resolve these kinds of problems as well. By we, I don't mean just Dask. I mean the larger, broader data engineering community. And this isn't just true. This isn't a problem that's inherent to Dask. This is a problem that's inherent to how the data world has shifted into these large cloud storage systems. When we have this problem of compacting many small files, so for folks here that have leveraged directory partition data or hive partition data, you'll end up with many small files. And optimization here is compacting them into a larger chunk. Again, these are things kind of outside the Dask world, but optimizations that the larger engineering machine within your organization is going to look for. And a terrible, terrible problem to run into is what happens if you are just leveraging S3 and Parquet, or any binary format or CSVs, is what happens if you're writing out your job, or the job is finished and now you're at the last step of writing, something happens and it dies. You run out of memory. Dask can help resolve those things, but a stray neutrino hits an EC2 node, and now you have partially written files. You now have a choice here. Maybe there's lots of ways to resolve this problem. You can rerun the entire job, which maybe that's not Maybe that's not too painful, or maybe that's extremely painful depending on the kind of job it was. Or you have to go through and manually find which files were corrupted. I believe Matt Powers has had the experience of probably trying to do all those and many more. So perhaps people here, when we open it up for discussion, can speak to these kinds of problems as well. And then now with GDPR compliance, right, the right to be forgotten. If you've built a service or you've built something that leverages public data, and it's all in S3, you don't have some higher level thing, or even actually if you have both, GDPR mandates that you go and delete that row. So how do we build a system that can now efficiently handle this? Again, it's not a Dask problem. Using just S3 and just Parquet is not enough anymore to handle these problems as we're scaling. So in comes these three potential solutions that we've seen in the marketplace. These are, I believe, all Apache projects. Maybe Delta Lake is not. And these are put up by larger companies. Netflix is working on them. Netflix and Google maybe are working on Iceberg. Delta Lake is being developed by Spark. I'm not sure who the major backers are of Apache Hoodoo, but these, Apache Druid as well. Yeah, thanks. Larger companies are looking at the kinds of problems that manifest with just these S3 Parquet plus a bunch of customizations and all these requirements from legal entities like the European Union. So to focus on one of them, but I think these are broadly true across all three, is that we can solve a lot of problems by just adding a transaction log, maybe on top of on top of S3. Or so Delta Lake has this transaction log, which is really nice. It lets us do time travel, which is always really fun to say, even though it's not as exciting as actual time travel. But we can go back and see a history of the database, and that's really critical. Like if you have some partial writes, you can resolve this thing by going back in time and looking at what happened when we added files 1 and 2, or we deleted files 3 and 4. This is, again, this lateral move that we've made from regular databases. We've been able to roll back things in database land for quite some time. As we went to S3, we needed those same kinds of solutions available to us. Yeah, this is like kind of the huge improvement that we've made on top of it. But there's a ton in the data lake space. I'm sorry that they've also kind of made globbing and file listing easier, made security a lot easier. They've resolved a lot of problems that we see when you just have the Hive metastore on S3, which maybe I'll leave it there, and we can talk more about this in the discussion time. So Dask wants to play in that space. We need better data lake integrations. There's already a PR up for Delta Lake, and we're talking regularly with the Apache Iceberg community. We heard a lot about metadata improvements that we're pushing into Parquet or into Fast Parquet and to the arrow readers inside of Dask. There's other file formats that we haven't talked about. I briefly mentioned ORC and Avro, but while those things are tabular, there's other binary formats that are popular in the HPC or the academic or ND array space, so mainly ZAR here. We could apply these same kinds of ideas to the metadata handling within ZAR, or maybe work more with that community and think about ways that we can leverage other kinds of metadata improvements to make fancy selection and indexing kind of faster or easier to spell for us as developers and ultimately for the end users. We've also been, we lightly touched on predicate pushdown. By that I mean, if we are trying to do a join on 2 Dask data frames across a couple columns, and at the end of this, we're only going to look at 2 columns, we can push that predicate, that selection of the kinds of columns that we need at the end, instead to the very beginning. So if if the user naively read in all of the columns at once from a large table, but at the end of the workflow, we only needed one or two, we can push that all the way. Dask can maybe develop some mechanism to say, actually at the beginning, only read in the first two, don't do what the user did. And again, SQL query, like database engines have been able to do these kinds of operations, and we're adding them to Dask. Yeah. So there's a ton of really great improvements inside of Dask. It's really great for ETL. The work is ongoing. We're deeply engaged in trying to improve things here, especially in the cloud space, and thinking about the future and integrating with these other data lake engines. And we have a new discourse room. I'd encourage everybody here to come to discourse for a lengthier and more detailed and, very importantly, searchable chat. So with that, I'd like to thank all of our speakers, Martin, Matt, Rick, and James, and open it up for a broader discussion.
And we have plenty of time, so please don't be shy. You can type in the chat and we can pick those up, or do participants have the ability to unmute themselves?
They should have, yeah.
Well, maybe we should continue the conversation that I'm seeing in the chat on the database versus data lake problem as it does to Dask. It sounds like as we scale up how we use Dask, we're discovering we need all the functionality that we get with a traditional database management system, plus all the things that it can do now. Do we need to eventually implement this kind of stuff? I was looking at the transaction logs that you were talking about there. And eventually, will we do it all?
Martin, if you, I have an opinion here, but maybe you want to go first.
Yeah. Well, the answer is sort of yes and no. There is an existing long thread or several threads about the handoff between SQL and Dask, and how much of your work can you push into the SQL layer. Obviously, you need to understand your database and have it optimized and all the rest of it, have it scalable for that to work. And it's definitely far from perfect how Dask interacts with it, but it's workable. So it solves some workflow. There's also the Dask SQL and Blazing SQL projects that implement SQL-like functionality on Dask, but Dask is not built specifically for that task. So I doubt that it will ever be as well optimized to very strictly SQL-like workflows, your typical join, aggregate type of thing. If you have your data in a database, it's going to do that better because it has lookup trees and all the rest of it to be able to do a really efficient job. And we can try to make Dask better, be able to do those things, but probably reinventing everything in Dask is not on the table, I don't think. It has been talked about, and in particular, I think Blazing SQL has gone a long way to do the query optimization part of that. I don't know, like Dask SQL also has done a lot. I don't know how far down the road it's gone so far. But Dask's power isn't that. It would be, it's a nice to have to use the same technology for all the parts of your workflow. Then you don't need to worry about deploying all the different pieces. But the more general that you make your tool, the less well it will be optimized for any particular part of it, right? So I would hope that we don't do it. I think that's my end opinion on that. Go ahead, Ben.
I would add not just that, well, for many things, Dask is not the, Delta Lake is a tool that's written by by Databricks. There's a reason that it is separate from Spark and that they work on tight integration. I think similarly, Dask is a really great tool and will have really great integrations between lots of other great database or data warehousing solutions. It's not, I don't think that Dask will want to eat the world and own all of those things. You'll want to have other projects that, like the rest of, I mean, arguably this is because, in my opinion, like the PyData community has figured out how to interoperate so well together that that's where the power from these tools come from. And similarly, Dask will interoperate with kind of tooling outside of it. I think we're also not best positioned to solve those particular problems, and that engineers at Netflix that regularly hit those problems are open sourcing their solutions for all of us to use.
Yeah, I think just to jump in here too. Oh, sorry, go ahead. Let me know when you're done.
All done.
I think, yeah, we can also kind of get the best of both worlds in some regards as well because of like query pushdown stuff. So I think like, for example, with the Snowflake connector, from what I understand, we can do like a huge join on the Snowflake side, you know, because huge joins, joining two huge tables is tough in the cluster environment. So we can do the huge join on the Snowflake side and then use parallel IO to send those results to the Dask cluster and then do our machine learning models on the Dask cluster. So I think that my vision of the future is kind of like the best of both worlds for some of these things based on where the computation should take place.
There is a question in the chat, just a general comment about where Spark is versus Dask. That's something that comes up a lot. And we can also talk about Ray, maybe if people are interested about that. But Matt, since you specifically touched the Spark versus Dask, do you have anything to say in this specifically Parquet at scale context?
Yeah, sure. Yeah, I think for most workflows, Dask and Spark are both great options for ETL type stuff. I think a lot of times Python people prefer Dask and don't like doing JVM type stuff. So my feeling is that they're both great. Obviously, Spark is a little different because it has the query optimizer. So there's some nice optimizations that Spark has that Dask doesn't quite have. But from what I understand, the query optimization stuff is underway and starting to get work on it in the Dask world. And James knows more about that than I.
We do specifically have a documentation comparing usage of Spark and usage of Dask. Doesn't go into low-level details.
Yeah, to give everybody some higher level context, the reason I switched to the Dask world is you can it's a lot easier to build customized stuff in the Dask world compared to the Spark world. You can build customized stuff in the Spark world if you're willing to write catalyst expressions, but that's really crazy and hard. And I was starting to mess around with Java bytecode, and then I was like, I don't want to do this anymore.
While we have a little bit of silence, I can comment very briefly about Ray, since I did just mention it. As far as I can tell, it may get to a place where Ray also performs general purpose computing workloads like we're talking about here, ETL type stuff and more flexible things. And I think it probably already can. It just doesn't seem to be the typical use case for Ray at the moment. For those that don't know, Ray is another parallelism system for Python. And it mainly seems to be directed very specifically by design at machine learning. So that's the goal that Ray has. Whereas Dask, again, interfaces with machine learning, but it isn't specifically built for that. It's a question about Xarray, which is something I'm also involved in. Xarray has an optional dependency on Dask. So you can choose to open your data sets backed by Dask, which means if you have a distributed cluster or a large machine, then you can get nice parallelism and out of core computation. As far as I remember, the way to trigger it is when you do X-ray open dataset. If you include chunks equals magic keyword parameter, then you will get a Dask backed data set instead of, it's still lazy. The non-Dask version is still lazy. You don't get the data for a particular array until you access it, but it will get all of the data in one go, which might not fit into your memory. There are quite a lot of examples of using X-ray with Dask, with videos of the dashboard and all that kind of thing, so you can check those out.
There's a question about Parquet sizing. Rick, since you've explored both GPU and CPU things, do you have any?
Yeah, sure. And as you mentioned, Ben, as you mentioned, yeah, so I work a lot with, I'm on the Rapids team, and so I spend a lot of time with Dask, cuDF, and things, and people who are reading in data sets using cuDF as the IO engine. And so for those cases, we usually want to have, you know, either the user will specifically design their data set to have something like 1 to 4 gigabyte files, so that each file will become a partition when you read it in. Or we'll just say, yeah, write really large Parquet files so that you can sort of scale that. And you can say, oh, I want to have 10 row groups per partition, or I want to have 100 row groups per partition, and just have like these giant, you know, 10 plus gigabyte Parquet files. And that seems to work fine. But something to keep in mind is that the default setting for read Parquet is that you will get 1 partition per row group. And sometimes that's a good thing, and sometimes that's really small. Sometimes, you know, if you just write out 1 file with 1 row group, which I think is maybe the default for things like PyArrow, this cannot, you know, maybe you can't, if you just write out one large 10 gigabyte file, that could be too big for processing things on GPUs. You might run out of GPU memory. So to go back, picking the size of the file to, you know, it depends a lot on the hardware. It depends a lot on CPU or whether you're using a GPU. And so I think we usually see files in, you know, under a gigabyte, just in case. But, you know, I guess maybe others who, because most of the time I spent benchmarking is using GPUs lately, so I don't have the best recommendations for what's the fastest thing in CPU. I think Martin might have the best idea there, but I would generally see files that are under a gigabyte for CPU usage. Is that right, Martin?
I think it's worth saying that whatever your workflow is, you're best off trying to evaluate and benchmark and otherwise analyze some subset before you get going on all of it. We used to always recommend each partition be larger than 100 megabytes. That's still in the documentation somewhere, I think. And that was largely born out of a question of latency when talking to IO layers. That might not be the thing that you're bottlenecked on, especially if you're using some of these tricks to aggregate multiple row groups into a single task, which is relatively new. So there are a few things to consider. There's the graph size, which will go as the number of partitions in your data set. There is the discovery phase, which will go as the number of files, because you need to read the footer of all of those files. There's the memory footprint of each of your tasks, which you can only really know by trying out a task on one of your partitions and profiling the memory use while that's happening. It's hard to know how much space a particular partition of Parquet data will actually need in memory, because it depends on a whole load of factors. So you should have an idea of what that is, and therefore how many partitions you can fit in memory at a time before exhausting your worker's memory, keeping in mind that whatever processing you're doing to that data will probably make some temporary objects while it's happening. So you should try it, you should benchmark it, and then double it or something, build a safety margin to make sure that your workers don't die at the critical phase 80% through your workflow. On actual recommendation, well, the trouble with Dask, this is kind of the killer feature and also the problem, is that Dask works well on a laptop, on a sort of 8 GB memory laptop with 4 cores. It works well there. And it also works well on a single monster machine with, I don't know, 500 gigabytes of RAM or whatever you can get these days. And it also works well on a Kubernetes cluster of 1,000 containers or whatever it may be. And probably if you're in a space to make choices, the choices that you would make to get the best performance will not be the same for each of those 3 cases. So yeah, measurement, I think, is key. I didn't give a number. I think less than a gigabyte is probably where I would sit.
I think that number might also change as you, depending on other contexts, like if you have local storage, or as we were just saying, if you're on S3, if you have many, many small files in S3, that might be really advantageous to pulling data from on many workers. What I've also found is that being able to experiment, like you were saying, Martin, is really useful. Many engineers in organizations will not spend the time experimenting and will bash their head against trying to solve this problem at another endpoint, or will just not experiment at all, or it's too hard to shift away from picking. Maybe the question is, if you were to pick a general size forever and you weren't allowed to move away from it, what would it be? That at organizations, it might just be, we just have 2 GB partitions, that's it. It's too hard to move all of the data to something else.
Yeah, what I would say moving forward is that it has become less important to choose a good file size as long as you have row groups that are a reasonable size. So in the past, people were coming to us running on things where they just had one giant row group per file, which is what I was saying before, where sometimes you just could not read in that data set if you're using something like a GPU, or you just don't have enough memory to read it in. And because that's the granularity at which you can create partitions, is at least one row group or a combination or a collection of row groups, right? And so as long as you have a small enough row group that you can, choose your partition as some number of row groups or pass in a chunk size, and we'll kind of calculate that on the, inside of Dask. As long as you have small enough row groups, I think you will be okay. But of course, if you're trying to, approach speed of light, then maybe the fastest thing you can do is to make your files exactly the size that you want them to be, and you kind of turn off all of the statistics gathering, so that all Dask is doing is just saying, oh, we have a file listing. Each one of these files is going to be an input, an output partition, and that will be your fastest scenario.
Yeah, it comes to the original comment that Ben made at the start, which is often if you face a particular problem and you figure out something that will solve it, like making your row groups bigger or smaller as it may be, you end up moving the bottleneck. You might not end up actually getting that much faster. So really figuring out where your bottlenecks are might be the thing. Like lots of files actually works pretty well now that FastParquet can fetch files concurrently, and you can aggregate them into tasks so that your task graph doesn't get too big. But you might find just listing the files to find out what's there is actually taking 10 minutes longer than the processing of anything. So it could happen. That would be for a remote, so S3, GCS, ASIO, or whatever, that is something that happens. But actually, it can just, if you're running on an HPC or other local cluster, it can just break because NFS doesn't support greater than X number of files in a particular directory hierarchy. That can happen too. So it depends a lot on the system that you're using.
One time I made a data lake that had 7 million files in it. and there were like lots of like 1 KB files. So I recommend not doing that. That was one of the slowest things I've ever done for optimal file sizes.
I did come across this as an X-array use case where data sets are often made by multiple append. And so one of the arrays in there was the time coordinate, but it had been formed by appending one time coordinate at a time. So it was made of 1,200 chunks, and each chunk held one individual number. And that was actually one of the first spurs to get the concurrent fetching of many things at a time, because each of these chunks, if you want to call it, that was like it's 16 bytes or whatever it was. And because they were compressed too, it was a single value, so probably 8-byte float or something like that, plus a compression header in each of those chunks. And they were being fetched one at a time over S3. So you had the latency of contacting the S3 saying, hey, I want this file, send me the file. Oh, by the way, how big it is. And then you get these few bytes, you decompress them, you have your single value. And you're doing this serially over 1,200, and it's taking like minutes to just construct this rather small array.
How did you find that out, Martin? Did the user say this is how the data is oriented, or did you look at a task graph and say this is really slow, I should investigate more?
In the X-array ZAR case, the chunking is easy to find, but I don't remember how we knew to look. It was just it's taking suspiciously long. So I probably used SnakeViz, and I saw that it was doing S3 fetch many times. That's usually how I approach something like that.
We should organize a materials on how to find the bottlenecks. And it's like all of these tools together to find that it's actually a data problem, or your chunk size, not chunk size, but like you have 1,200 chunks of one data type. Yeah,
so Dask provides you a lot of diagnostic information, but sometimes the best way to figure out why something is slow is not to use Dask, so that you can directly delve into the internals of what's happening.
I know, that's actually one thing I'll mention with the Dask versus Spark comparison. So one thing I noticed coming to the Dask world, the diagnostic information is just so transparent. So like for me, like PySpark clusters were always a bit of a black box, didn't really know what was going on. Whereas with Dask, like those task graphs that Rick was showing, you can really understand what's happening in your cluster and can identify bottlenecks easier. I just found Spark to just be, they have cluster metrics, but I just didn't ever find them to be as useful as the Dask ones.
So an interesting question just came in about how much data you can pass between tasks, which is a different kind of partition size, if you like. And there isn't a technical limit, but if tasks are being run on different workers, then that data will need to be serialized and communicated from one machine to another, or from one process to another. That still needs serialization of some form. So it does matter. Dask tries to move the compute to the data. So whether something will be copied from one worker to another does depend on the size of that data. It's one of the heuristics that's used, and Dask will try to schedule a task that needs a result to the worker that already has the result, so that you don't have to do the serialization and copy and transmit. But it happens, and that is something that is clearly shown in the diagnostics page. And it will depend on, again, a bunch of things. It'll depend on the amount of memory you have available and the communication speed. For shuffle type workloads, you generally have to do this to some extent. However, shuffle does tend to chop up your data into lots of small pieces. So probably the size of the pieces is not the limit in that case, but the sheer number of pieces is the limit. I don't think there's any particular extra things you have to think about aside from memory footprint. So if you copy something, then you will be using at least twice its memory at some point on the original worker and the worker that's receiving it, plus overheads for turning it into bytes, which can be quite efficient. So serialization has moved on quite a lot in the last couple of years. So you don't necessarily end up with many times the original memory size, but you might. So it's another thing that you would want to measure. But overall, partition size arguments will be the same as for reading in the data. So you need to care about the size of it versus the global memory that's available. If your machines are not co-located on a cluster, then obviously transmit times will be much longer. So you might care more about absolutely trying to reduce those sizes if possible. Typically that comes down to compression or a better algorithm that just doesn't do as much passing around of data. Serialization of pandas does now use arrow, is that right? I'm actually not sure anymore.
Dask has a variety, or broadly answer the question, Dask serializes things in a variety of, through a variety of mechanisms, Pickle 5, arrow. It does some fancy serialization for GPU things.
It's pluggable, as well as using the standard Pickle architecture. So if you have some objects of your own that are not known to Dask, you can use standard Pickle ways to define how it gets serialized. But you can also submit specific serialization types to Dask so that Dask knows about them and does the right thing, specifically for the case of sending it from client to worker or worker to worker.
Maybe James, could you answer the question on handling S3 connection limits?
Yeah, for sure. So there's a couple of different, so yeah, retries is right now an answer to your point. There are a couple different levels at which you can retry things. So Martin can probably comment on S3FS has its own built-in retry with exponential backoff or some backoff mechanism. And Dask also has its own independent of S3FS back or retry mechanism as well, where you can say, hey, you know, like run all these tasks. If any of them fail, like keep retrying them up to user defined amount of times. I think by default it's 0 maybe, and feel free to retry it up to say 10 times or something like that. There's a question as to tuning these retries to make them sort of effective where you, at the level that users don't actually have to specify anything manually. They just take care of themselves. But yes, that's hopefully answering the question, Brian.
There is also a third lowest level for network type stuff that people don't tend to have to deal with, but it can be a problem if you're running things from your laptop and reaching out to a cloud service. Then you can have network type things, interruptions, whatever. I haven't heard much of people specifically requesting for that style of retry. But yeah, as I say, there's a load of conversation around this and exactly how to best expose the communication layer retries and what they mean and the different kinds of retries is an open problem, I think. On consistency between types of arrow versus pandas, or I should say Parquet versus pandas. When you write using either arrow or fast Parquet, then we translate the data to Parquet appropriate data types because that's the only way we can get Parquet to store them. But we also store in the metadata of the file a description of what the original data type was, which enables us in most cases to round trip the data perfectly, including things like date time zones, which is something that comes up and generally I think works pretty well. Some things that just can't be stored or some things that are optional, I'm thinking particularly of categorical data, is an interesting one. So Parquet supports what it calls dictionary encoding, but it's not the same thing as asserting that your whole column is a categorical type. So that is something that we put some effort into working around. Dask doesn't really have its own data types. It just uses whatever the Python library of choice uses. So that would be the pandas stroke NumPy type system. And the same thing goes for cuDF or whatever other libraries. They are mostly consistent with each other. Pandas has come up with a few new data types recently, the nullable data types, that kind of thing, that are not necessarily standard. So there are some options that we might do surface in some places, or not necessarily, depending on how new they are and how standard in pandas they are. And that means when you come across Parquet data that could be represented in one of these types, either you need to add yet another keyword argument for the user to be able to choose if the user recognizes that this is indeed an option, or you try and make a sensible guess. So it's something we're stuck with, I think, and we try and make reasonable defaults. We try and document the differences, and we try and keep up with changes as they happen.
I think to add to that, it's hard to be consistent because people want they want D-type specific for their applications because they can get some kind of optimization from it. So for example, cuDF recently added decimal 1632 and will soon have 128 data types, which will just not around for pandas, but is available inside of Arrow. Probably FastParquet can get it.
And there's also the other way that cuDF does not support nullable data types, I believe, whereas pandas does now. And so just kind of aligning things and assuming nullable data types from Parquet into pandas can break things in cuDF. So it's hard to coordinate all of these different types.
It'd be better if we could agree, if the world actually at large, not just PyData, but also PyData including R, could agree on null handling. They're starting at that level and then going to other data types.
Yeah, good luck. Just talk to the sparse people.
Yeah, and then sparse.
Yeah, and I don't want to say anything about ODBC. ODBC works over text, actually, so that the specific database drivers may be optimized and have a more opinionated view on data types, but anything that sends its data around in text, in JSON or whatever, you will lose type information when you do that. So it's a best effort kind of scenario. I don't think Dask itself is in a position to do anything about that. It relies on other tools. So we have 10 minutes left. So there's still quite a few people in this meeting. Please raise your hand, type in a question or whatever. Yeah, text. I mean, it's still ubiquitous. I know we talk a lot about optimizing for Parquet and other binary formats, but it's still true that CSV is probably by volume the biggest data store of raw data for tabular data for any data. But there are other things like JSON and XML and I don't know what, that if you're demonstrating how good your data processing system is, you wouldn't use those as your benchmarks, but in practice, lots of people have to deal with them.
Okay, we still have some few minutes, but while the chat can come up with some last questions, I would like to start with thanking you for your talk and for all the questions you answered today. I think we had a great, vivid discussion in the chat.
Yeah, thanks everybody for being a great audience. This is a great, lots of great questions.